So now let's see how to implement the noise, the AWGN channel. So in this part we will create a vector of noise by using the random function, and the strength of the noise will be determined by the SNR value that we specified before. This SNR value is in dB, so we have to map it back into the linear scale by using this equation. So this will give us the variance of the noise that we need to generate, which will determine the strength of the noise. And also the noise vector will have to have the same length to the length of the signal that we want to transmit. So to generate the noise, we use the random function to generate random numbers. So since we want the noise to be complex, we will generate twice, like one for real part and also one for imaginary part. The one for imaginary part will be multiplied by j to make it imaginary. Also, as I said before, the random function generates the random numbers with variance of 1 and mean 0. So in order to scale this variance into the one that we want, we have to multiply this whole thing by the square root of the variance that we just calculated here. And also, since here we have two components, the real and imaginary, these are two independent random vectors. In order to make sure that the effective thing that we are generating here has the variance that we want, we need to normalize this thing with square root of 2. So after implementing this step, we now have the noise generated that we can add to the signal that we want to transmit to get the received signal. But before we move to that step, we can do some simple analysis to analyze the signal that we have just generated. So the first thing that we can do, let's see if the ratio of the signal of the power of the signal that we want to transmit to the noise power is the one that we desire. We said like we want the SNR of 10. If you can remember here, we specified we want the system to have SNR of 10. So let's see if we are getting that. And to do that, we can simply calculate the signal power by taking the absolute of the TX signal that we generated, square it and take the mean of it. So this will give us the power of the signal. We can repeat the same thing for the noise, and we will have the noise power generated. So to calculate the actual SNR in this system, we just take the signal power divided by the noise power and then convert it into dB scale. That will give us the actual SNR that way. So let's see and if this actual SNR matches with the desired SNR. So we will run the code to see that. So we can see the actual SNR is not exactly 10, it's 9.9 something. So we want you to investigate this and comment out what could be the reason for this discrepancy. We will mention this in your report. Now let's see something else. Let me put this back. Now let's analyze the PDF of the noise that we generate. To analyze PDF, we can simply plot the histograms. But because the noise is complex, we have real and imaginary parts, so we will find the PDFs of each part separately, and then we will also plot the joint PDF for both real and imaginary part. To do that, first we transpose, because the noise that we generated is in the raw vector, and to calculate the histogram, we need the column vectors. So that's why we are doing this step here for real and imaginary part of the noise. And also we need to specify the number of bins, like the number of bins that we want our noise samples to be sorted into when we are plotting the histogram. And we will use the heist command to plot the histogram for both cases. So let's see what we will have in this case. So here are the results. As you can see, this is the real and this is the imaginary part. As we can expect, we say like the function we use to generate the noise generates the noise with a Gaussian distribution. So, and we can see this histogram, the PDFs of the real and imaginary part, they somehow follow the Gaussian distribution with zero mean, as we could have expected. So this is fine. Now let's see the joint PDF, how to do that, which is the next step. For this part, we will use the heist3 command, and we will put both the real part and noise part, as you can see here, and we will specify the number of bins for both of them as we specified before. I will go and plot this again and see what we will have. So as you can see here, we have the 3D figure, like for the imaginary part and for the real part. In both cases, the mean is 0, as you can see, and also you can see from this direction, from the imaginary part perspective, if we can change, we can somehow change this. We can see here we are seeing the Gaussian shape. Also in this direction we are having in the real part side also we are having the Gaussian shape. So that means we are doing everything correctly. Now we can move on to another step. Now we need to see the autocorrelation of the noise, how it looks like. To do that, we use the xcore function. Normally this function does the cross correlation. That means the correlation of the two different signals. In that case, you need to put two inputs here. When we put one input, that means it does the cross correlation of the same signal, which means it is the out correlation. So and the output is going to be the delays and the values at each delay. So we will also plot the autocorrelation, and to plot that we use the delays and the values that we are getting, the absolute values of the value that we are getting. So we'll plot that one as well. Here it is. So we can see here what we are getting. We are getting the maximum value at delay 0 when the lag is 0. But anywhere else with any other lag, we are having almost 0 values. So we also would like you to comment on this, why we having this kind of behavior. We want you to comment on this and put it in your report. So after this, we will now go and see the received signal in the next step, what we are receiving and how to analyze it in different domains.